All right, everyone, welcome. Hello. First off, a couple of administrative things. One, exam is not graded, and I actually haven't started grading. To be honest, I've been too busy, but I did take a little spot check through them and pleasantly surprised. So overall, from what I've sampled, I just randomly sampled people's exams and looked at a couple problems. I think overall, I also looked while you guys were taking it. I looked at people's and looked at the looked over shoulders. I think overall, I am happy with how people did. I think presumably you guys will also be pleasantly surprised, at least for the most part. I think it will be at the very least a higher average. We'll see how much higher. I haven't graded it yet. Okay. So, oh yeah, a couple other things. One, Friday is going to be a lecture. Friday is a Monday schedule, so it's no discussion on Friday. Also, I haven't released Project 3, which I have heard 0 complaints about, so I am planning to still release Project 3, but now that we are planning to drop Project 4, not to do Project 4, there's not a particular rush. I likely will release Project 3 on Friday, but no guarantees. I have a very busy schedule. I'm teaching until 11 tonight. Sucks. Anyway. Oh, one last thing. Sorry, I forgot I had a lot of administrative stuff today. One last thing is we looked through Project 2. We're going through we're grading that before the exams, just so you know. And quite a lot of LLM answers, to be honest. Oh, I got quiet. So just so you know, for one, it is I know that there's no really clean detection tool or method that gives 100% accuracy, but sniff test is usually pretty accurate on this stuff. What I'll say about it overall is I know why people do that sort of thing, that is cheating or using an LLM when I tell you not to. Almost always it's a result of stress more than laziness. I'd say 90% of the time it is, I'm so stressed, I have this deadline and I need to finish it, so I'm going to do it this way rather than the other way. I understand that, I can empathize with that. I try to design in such a way that isn't to happen, and so that it gives you enough breathing room to work on these projects. And you can see the amount of leniency I give in a lot of other ways in this class. I will just give you a statistic that should maybe be informative. Right now in high school in America, the average high schooler reads at about a 4th grade reading level. And a lot of this, you can't do basic arithmetic too. A lot of this is attributed to over-reliance on technology. People are increasingly in the academia sphere talking about brains atrophying, people not being able to solve these problems. I would hope that for all of you, just self-reflect, think about what type of person you want to be. Do you want to be a Wally chair person, or do you want to be someone who is, expanding their brain with these tools and is actually reaching the new heights that we're reaching? We're getting a whole bimodality. People are becoming smarter, but people are also becoming dumber. Be on the right side of the curve, my recommendation. If you're here at least, try to be on the right side of the curve. Okay, that's my spiel. We'll figure out what to do about it. It's sort of annoying for us to deal with, but just also know it's obvious, I suppose, also, so that you don't, higher barrier to entry, we can tell. It's just whether or not we're going to do anything about it, and we're still deciding. Anyway, all that, now, new topic. So we finished exam 2, we're moving on to a new topic, and this is an interesting one. We're going to get a little taste of the deeper theoretical side of algorithms. And it's an interesting topic, and if you want more of this topic, there is a lot more of this topic. The 501 in particular, if you're interested in this, if you enjoy the next couple lectures, that's a class to check out. The next 2 lectures are going to be on complexity classes and reductions. Those are going to be sort of the way DP was the meat of the previous exam. This will probably be the meat of this exam, although we are going to have some extra topics at the end. We're going to do one lecture for a bunch of different miscellaneous topics since we have a little bit of time. And those will also still be tested. Now, throughout this class, we've been doing runtime analysis. We've been doing this big O notation. And it's been taking a whole bunch of different runtimes. Right? You could have like n squared plus n, da 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 da, or it could have 15n squared or whatever, and we're bunching them together. We're saying all these things are all O of n squared. Doing this allows us to describe different algorithms. It allows us to create sort of groups of runtime. It allows us to compare things very nicely. It's a sort of good analysis for us. Furthermore, sometimes we've seen things like we've said, like n squared, maybe n cubed, maybe n to the 15th, and all those things I've called offhandedly polynomial algorithms. That is, they run in some polynomial of n. It turns out that it is a pretty good idea. It does give us some value to be able to group these sorts of algorithms together. To say, this sort of algorithm is doable in this sort of runtime. Maybe it can be done in logarithmic time, maybe linear time, maybe polynomial time. In making this distinction, we can group a bunch of different problems together to make different, what we call complexity classes. Now, if we take this and we look at sort of the state of these groups, it looks something like this. Give a second for it to pop up on the screen. This, by the way, is a diagram made by a professor of mine, actually, at UMass, Neil Immerman. This is, if you want to look it up online, it's called descriptive complexity. He is the father of that field of research. And this is his diagram. You can get it on a shirt if you want, by the way. Now, you'll notice a couple of things that we talked about. So we talked about here, P, polynomial time. But you may also notice that there's a couple other things on here. So this is obviously a very dense diagram. It's very hard to parse. But these are the sorts of groups that we find in nature, I suppose, to problems that we care about. This is a natural way for us to maybe group them. And you'll notice this is a very intricate way to look at these problems. We, in this class, are going to focus just on this little barrier right here. Okay? So everything else we're not going to talk about much. We'll talk about it lightly, but we're not going to talk about anything below this line, really. There is a lot of interesting theoretical things going on here. A lot of this is things expressible by different languages, which is an interesting thing to think about. Up at the top, we have things that are not doable by computers. So we have a lot of interesting things going on here. These, by the way, in black are the names of the complexity classes. If you're curious, you can look them up. P, NP are ones that you've probably heard before, and those are going to be the focus of this class. We also have some other interesting things here. These, don't worry about them. If you're curious, you can Google them. Those are a little bit what I was getting at of different languages and things expressible with those languages. So this is first order. Is what FO stands for, in case you're curious. Okay, so there's a lot of different ways we can separate them, but there's pretty natural ones. For example, we have here is polynomial time. We've talked about that already. We have a good idea of what that is. We also have exponential time, so algorithms that are doable in exponential time. We have NP, which we'll talk about in a moment. And we have like exponential space. We have polynomial space. These are interesting things. We're not going to talk too much about the space classes, by the way, but you have your intuition of what that means is not super far off. Okay, cool. Any questions on this diagram before it goes away? If you end up taking a class like 501, you'll probably see this again, by the way, and you'll actually have to digest all of it. Okay? Any questions? No curiosity? Okay. So, now let's talk about the classes that actually matter for this class. So, the point of showing you that is just to show you the depths that this can go and the complexity of this area. This is probably what I would personally call this sort of theoretical analysis the most difficult thing in computer science, personally. So just so you know, I mean, some people really love it, and if what we talk about in the next couple of days really works for you, I would look more into this because there's a lot there. There's a lot there. Hey, you missed this diagram if you want to look at it quickly. Wow, impressive. Okay, moving on. So we're gonna focus first on two classes, and then this is going to expand a little bit. Okay. Well, I'll add an extra one in there actually. So I don't know oh, they're right there. Oh well. So First up, polynomial time. Polynomial time is our bread and butter. Can anyone tell me what polynomial time means? And this is also labeled P often. Okay, what's polynomial time? I've just said it, so you can feel comfortable answering it. Yeah? Yeah, so we're generally going to use n as our variable here. I'm going to see if there's a better marker, by the way. This feels a bit dry. So this is going to be, most appropriately, we're going to say this is problems solvable in O of n to the, I'll say p. Maybe that's bad, actually, it's np. N to the c, let's say, where c is some constant. Alternatively, I could also write this as, I'll write it this way because it's more appropriate, O to the 1. So it's n to some constant. Make sense? Is what polynomial time is. So if I have a problem and there exists an algorithm that can solve it in O of that, then I will call that problem in the complexity class P. Okay? So I can say that problem is in P. Cool? Cool. We also have another one that we know and love, which is linear time. Ironically, this is not L. It's most appropriate. I'm not going to put its name because it's just going to be confusing. Linear time is going to be just O of C times N. There's going to be some linear thing. That is, as we've seen before, we can chop the C. But it's going to have some runtime that is just linear in N. Cool. There is, of course, also logarithmic, and you might have noticed at the bottom there is log logs and log log logs and so on. There's a whole hierarchy of them. Don't worry about that. But these are ones that we're going to talk about in just in the quiz today. Polynomial time, linear time, exponential time, which is actually the name of it is x time, exp time. And this is anything that's going to be O of something to the n. Okay? So that's going to be exponential time. And lastly is going to be the most complicated of each of these. So each of these should make a lot of sense. Again, the one thing that is a change of mindset is this is referring to problems. So different problems are in these complexity classes, not algorithms. So if I have a problem, if I have a problem and I come up with a linear time algorithm to solve that problem, then I say that that problem is in linear time. Okay? By the way, just a yeah, sure. Question? So O1 just means something that is constant. So it's n to the power of a constant. If I just put c there, I put c in the other two places because it's a stand-in for constant. Same I could do there. I could say n to the c. Yeah. It's just, this is the most appropriate way to do it. Yeah, cool. So, as a consequence of this, can someone tell me something about an algorithm, a problem which has linear time algorithm to solve it? Which complexity class is it in? So if an algorithm has a linear time, if a problem has a linear time algorithm to solve it, which of these complexity classes is it in? Give everyone a second to think about it. Yeah. So it will be in polynomial time also. So the obvious answer here first is linear time. So if there's a linear time algorithm to solve a problem, then I know it's in linear time, the class linear time, because that's the definition of linear time of that class. But it's also in polynomial time because this, you'll notice, is just an upper bound. So something that is linear time is upper bounded also by polynomial time, right? So in fact, the structure of these classes, and by the way, is it in exp time? It is also an exponential time. Exponential time is greater than polynomial time. Right? If you remember from our asymptotics, this is larger than this. okay, asymptotically. So in fact, we have, and you'll start to see where this diagram comes from, we have at the bottom here linear time, and above it we have polynomial time, and above it we have exponential time, and anything that belongs to linear time also belongs to polynomial time and also belongs to exponential time. So these are like, you could also imagine it sort of as spheres. So this is like linear, this is polynomial, and then this is exponential, right? So as I increase the allotted runtime for my algorithms, the amount of problems I can solve increases. So the class exponential is strictly larger than the class polynomial. Yes? Yes, sir. That diagram is not even a complete diagram, by the way. There is a lot of nitty-gritty in here. There's a lot of, and you'll find that it's actually very well studied, these problems, strangely. If you look into it, I'm absolutely, especially that sorting, that's obviously studied really well. Yeah?
So that diagram.
It would be more appropriate to say that linear time, the set of problems that are in linear time, is a subset of things in polynomial time. And in fact, is going to be a strict subset of, we know. Okay? Cool, does this make sense? So these are at this level of complexity, classes should hopefully make sense to you. It is, as I allow more and more runtime, what problems could I solve in that runtime? And there are problems, in fact, that we can prove are in exponential time that are not in polynomial time. That is, there exist some things that are in this region, there exist some things that are in this region. Okay? So for both of those, we've proved that. We know that there are problems that I can solve in polynomial time, but I cannot solve in linear time no matter what. We've proven this theoretically. And same with exponential time. And that brings us to our most interesting complexity class that we're going to talk about today, which is non-deterministic polynomial time. So this it's called non-deterministic polynomial time. Give me a second to write that. Non-deterministic polynomial time. And this is the class NP. So hypothetically, you've heard of the classes P and NP. If you haven't, they are a very famous set of classes, and we will see why very shortly and in the next couple of classes. So non-deterministic polynomial time, NP. Anyone want to guess what its runtime bound is? Sure. No. Anyone else?
I think it's P.
You think it's P? Okay. Fair enough. Yeah. So what's interesting about the class NP is that it does not have a bound like this. All of these are this sort of bound. There exists an algorithm that runs in this time that solves a problem on a deterministic computer, on a deterministic Turing machine, if you will. Hopefully everyone is comfortable with me saying that, but on a classical computer. Non-deterministic polynomial time is O of NC, right? It's polynomial time, N to C, on a undeterministic, a non-deterministic Turing machine. Okay. How well do people remember NFAs? The thumbs up if you remember NFAs and you're comfortable with them. Okay. Non-deterministic finite automata is what they stand for. It's from 250. We had DFAs and NFAs, if you remember that. Some people are starting to remember. So the way that a non-deterministic finite automata, I will draw it briefly. I'm not going to lecture DFAs again. But basically, we had a machine which has some starting position and then has, each of these are states, each of these here. So you'd have something like that, and then maybe a B can loop, and then maybe this goes to a new state. Everyone remember this now a little bit? Okay, and maybe we'll have a goal state, and maybe this is C. So with a DFA, we would follow these arrows, and then if we ended at a goal state, we're good. An NFA allowed us to have duplicates of certain, like from any node, from any state, I could have two different paths that use the same next input, and then if any of those reached the output, the goal, then we say that it's accepted by the NFA. This is the same sort of logic. I'm not going to get into it too much. I think it's maybe not worth the time. Again, if you're very interested in this stuff, take 501. There's a lot of more of this out there. Essentially, it's the same sort of logic, but with a Turing machine. So if any of the Turing machine is, I can run polynomially many Turing machines at the same time. If any of them could get the correct solution in polynomial time, then I have a solution, and I say that it is solvable in polynomial time with a non-deterministic Turing machine. Okay, weird thing to try to conceptualize. Luckily, some other people have done a lot of legwork for you and come up with a much neater way to define NP. So this is what it really is. This is what you should think of it as, like if you are, if you're really reckoning with it. But for this class and for our ease of conscience, we can also define the class NP to be the class of problems which, when given a piece of information, can be solved in polynomial time, can be checked in polynomial time, let's say. So for example, if I were to, I'll give a dumb example, but you'll hopefully you'll see on the quiz some more real examples. Let's say that I want to sort an array. Clearly, sorting an array you can do in polynomial time. Don't worry about that too much. But if I were to take that array, and then I could say, okay, here is the correct ordering of here is a sorted array. So I can say I give you the original array, and I also give you the sorted version as a hint. Then how long does it take you to check that hint to make sure that it is correct? So if that checking can be done in polynomial time, then we say that it is inside the class NP. Now, can anyone tell me something about the relationship between NP and P? Where does it go on this diagram? Yeah?
I guess it goes.
So it's going to be exponential time. What do you mean by that?
Like it's gonna be.
Okay. So here is how we add it to our diagram. So in fact, if we look on here, so I'm going to add, I'll add red because I think it's going to be, or maybe I'll do green. Green. Let's do that. So NP is going to go right here. Oh, nope. It's not going there, I guess. I need to get rid of these ones. It's going to go right here. So in fact, any problem that can be verified and solved in polynomial time can clearly, like anything that can be solved in polynomial time can obviously still be solved in polynomial time if I give you a hint, right? So I can still just, the verification would be just solving the problem. I'll probably repeat this in a little bit, but again, non-deterministic polynomial NP is a class of problems where if I give you the problem, and then I give you a piece of information, it has to be polynomially sized, but that's neither here nor there, polynomially sized hint, right? Then can you verify the solution to the problem in polynomial time? So there are some somewhat famous examples of this. Let's imagine that I want to find I didn't put it on this one actually. Okay, let's imagine a problem where I want to, I have a graph and I want to find the path that visits every node that is shortest. Okay? So I have a weighted graph, and I want to find the path that goes to every single node that is overall the shortest. Okay? So this is close to minimum spanning tree, but it's not minimum spanning tree because it is an ordered, I have to go to every node, right? And I go from that node to somewhere else. So that problem is famously a difficult problem, and in fact is in NP. So if you were to take that problem, right, I say here is a graph with all of its weights. I want you to find the path that goes through all nodes that is shortest. Then my verification, I could give you that path, and then you could check that that's the shortest path in polynomial time. Okay? Do people understand? That problem, by the way, is called the traveling salesman problem. It's a very famous problem. Do people understand this? I'm getting a little bit of blank stares. I would like some questions to help me gauge where you're at. Yeah. Go ahead and try. If you do, you win $1 million. Yeah. Yes.
You just say
The class of problems, or
like it's a class of problems.
yeah. So NP. This bears repeating. It's good. NP is a class of problems where if you're given a hint, let's say you're given a solution, is generally what you'll see, but it could be any hint. But generally, you're given a solution that you can verify that solution in polynomial time. Yeah. Yes.
So what's like?
So you could give just the path. You could give the minimum path, and you can. It is somewhat tricky to show that you can go through that path and show that there is no better path. It's easier to show there's no better path than the path you're given than it is to search for that path. Or it is maybe easier. So what's interesting about P and NP, and the reason that they're such a famous set of classes right now, is that this area in between them, this here is NP, this is P, it is unknown whether or not there exists any problems in here. And in fact, it is hypothetically provable that there exists no problems here. So the question remains that either P is equal to NP, or P is a strict subset of NP. And it is unknown which of these is true. So you asking the question, could I just solve it in polynomial time? It seems like I can. We don't know. I can't tell you. And in fact, this is a very famously unsolved problem. If anyone is able to answer this problem, you win $1 million. And in fact, we are going to develop all of the tools you need to try this problem yourself. And you are very welcome to. Yeah.
Where did exponential?
So exponential is on the outside still. I just erased it. Exponential is strictly larger than the others.
Oh, okay.
So what we have here is, to give you the, I'll remove the non-deterministic Turing machine. Not particularly enlightening, actually, but if you want to understand what the class actually is, that is what it is. So what we have on here is that linear is a strict subset of polynomial, which is maybe equal to NP, which is a strict subset of exponential. That's what we've shown that's what we've talked about so far in class. And these are the only classes that we're going to really focus on. Caveat: we're going to talk about something else somewhat similar, but these are going to be the main stars of us talking about complexity theory. And we're going to show how we can show that things are in each of these classes. And primarily, we're going to be talking about these two. Okay? Any other questions on this? Yes?
So you say that.
Basically. So it's a slightly more nuanced thing, and I've done a little bit of complexity theory research that has run into this, so I'll tell you, it is slightly more complicated than the answer can be checked in polynomial time, but that's basically it. And I think everything that we're going to talk about in class, that is an appropriate way to check for NP-ness. But it really is given a hint. So it's any piece of information, and we're allowed to choose what that information is. Then we can verify that if we do that verification in polynomial time, that the information is correct, then we're good. Yeah. If after that information we can get the answer. Yeah. Okay. All right. All right. I think with that, if there's no more questions, Amanda. It's like normal algorithms. So when we've done all of our complexity analysis, when we said something is n squared time, that is on a deterministic Turing machine. Every time we've ever said anything about runtime, anytime we've ever said it in this entire class, we've assumed that we are on a normal computer. NP is a weird class, and you can see why it still is an interesting class to talk about, even though this is like not a realistic thing to have a non-deterministic Turing machine. They cannot exist in the real world, at least to our knowledge. But the reason that they're interesting is it asks this fundamental question: is it easier to solve a problem or to check its solution? Is it easier to make a maze or solve a maze? This is a problem that it turns out a lot of interesting problems ride this line, where they are known to be an NP, but it's unknown if they're solvable in polynomial time. There's a lot of very interesting problems that are in that range. We know that they're in NP, we don't know if they're in P. There's a whole class of problems, and it turns out it's a class of very interesting, very like real world applicable problems, and a whole bunch of other theoretical results also ride on the idea that either P is equal to NP or P is not equal to NP. So there are both theoretical results that rely on each of those. So the reason people care about this, as soon as you solve that, one, we are enlightened somewhat about the state of the universe. Is it easier to solve a problem or check a problem? Is something that's unknown in polynomial time. And secondly, a whole bunch of other theoretical results will be proved true and proved false simultaneously. You're gonna weed out a whole bunch of noise in academia, which is also very nice. Yes.
So, problems like the traveling salesman, do we know that?
Yes. Okay. Everything in NP is solvable in exponential time. Yes. So NP is a strict subset of exponential. Okay. Cool. By the way, there are things such as non-deterministic linear, by the way, just so you know they exist. A lot less interesting, and we can say a lot of different things about them, but this is the interesting one. That's why we're going to be talking about it. Okay? Any other questions? Okay. Try the quiz. Give it a go.
You're saying like people running an algorithm, sometimes you do the thing in the same case you do anything.
So you can imagine it, probably the easiest way to imagine it is imagine many programs running at the same time. So instead of just having a single algorithm, I write some polynomially many algorithms. And if any of them can solve it, then I say that it's solved.
But isn't that just how a normal algorithm is anyway?
No. So you can imagine
Because if you're running many algorithms,
imagine for sorting, right? I've got a bad example for actually like an interesting example, but you can say one of my algorithms will choose the first element to be the fifth of my list or whatever, right? And it'll have some strategy there. And I'll have all those different sortings, right?
Yeah.
All in linear time, right? They're just like choosing arbitrarily like this. And then if any of them get the correct sorting, then I say that the problem is solved. So this would be on a non-deterministic Turing machine, sorting could be linear time. You see what I mean? Okay. You can sort of just imagine in your mind a whole bunch of different computers, all with different algorithms. And then if any of them get the correct answer, then I say that it's solvable by non-deterministic.
they all have different algorithms, and if it's solvable in any of them, then why not just use that algorithm?
Because not every problem is going to be solvable with a single algorithm.
I see what you're saying.
Yes, different inputs would be solved by different ones.
Okay.
Yeah. That's what the sorting example is supposed to be. Simple path. Does it not say simple path? Okay. For longest path, it's a simple path. It only visits each node one time. Yeah. Okay. So I'm going to point something out real quick for everyone. It is possible for some of these problems to be in multiple complexity classes. It is also possible for them to be in none of them. Now you may discuss with your team, discuss with people next to you, and see if you can figure that out.
The first one would be in polynomial classes that if they're exponential numbers. Second one, exponential. That was the longest class. Yeah. Okay. I'm not sure. Well, you can only generate being given a solved I know this for you. Like the only way you can generate a consistently is by creating a valid input for anything. You can't generate it. Exactly. Yeah. No, that's it. It's an unsolved question. I'm working hard on and it's long term running. It's just long term. We don't know. Oh, yeah, exactly.
We don't have any way to file the
What's the hint? What's the hint? The hint would be a pass. Just like, yeah, in the version of my 250 it taught us and I didn't do 250. So
Okay. Okay. Ready off there. So let's go through these. Let's see. As many of you have now noticed, it is a near strict subsetting. So if something is linear, then it is also polynomial. If it's polynomial, it's also an NP. If it's NP, then it is also exponential. So what I'm going to do for checking what people feel of here is raise your hand when you think it is something, and I'm going to count down from exponential down to linear. So put your hand down when it is no longer in that class. Make sense? Okay. So, for example, sorting an array. Is that in exponential time? It is. Is it in polynomial time? Is it in NP? Is it in polynomial time? Is it linear? It is not. So the runtime, as we showed, n log n, you may have been thinking something like radix sort, which I believe you said, something that does run. There are linear time sorting algorithms, but that is not the general problem. That is only for integers or some other subset of numbers. I just said numbers, which makes the problem a lot harder. Yeah. Okay. Your question? Or yeah. What? What? That solid sort, by the way, is so it would not be considered a sorting of the array. So that would be a sorted subset. Yeah, if you don't know that, by the way, if you've never heard of that, Stalin sort is when you go through the array and anything not in order you remove from the array. Which would in fact be linear time, but is not sorting the array, unfortunately. Yeah? Quantum bogo sort is getting a lot closer to non-deterministic to Turing machines. It's not on a Turing machine, so no. Okay. Next up, shortest path. So to clarify this, there was some confusion about this. This is finding all of the paths that start at S and end at any other given node. So they don't necessarily overlap. It's not finding a single path through all the nodes. It's finding the shortest path that starts at S and goes to each node individually. We have seen this problem before. This is not traveling salesman problem. So raise your hand if you think it's exponential. NP. P. Linear. Very good, very good. The runtime of Dijkstra's, which is the algorithm that solves this, is O of V plus E log V, I believe, which is very similar to sorting. It's the same sort of thing. It's polynomial. It's nonlinear. It's above linear. It's above linear. It's polynomial in E, or in V, I guess I should say. Next up, longest path. So this is finding the longest simple path, that is, it does not repeat any vertices along the path, and it has to be the largest one. Who thinks this is exponential time? Who thinks this is NP? Who thinks this is P? Who thinks this is L, or linear? Okay. We have a question mark here because this problem is famously in NP, but unknown to be in P. So we don't know. We don't know. So this is in fact, we'll talk about this problem later on and how we know that, how we know it's in NP without knowing that it's in P, but we do in fact know that. So you can show that there is no longer path. If I give you the longest path, you can show that there is no longer path in polynomial time, but it doesn't necessarily take that long to figure out the longest path. It might take longer, it might take polynomial, we don't know. Okay, next up, Sudoku. If people aren't familiar with it, I'm going to assume people are because I didn't get any questions about it, but it's a number game where every row, column, and box has only one copy of 1 through 9. You're given some of the boxes filled out, and then you have to figure out all the rest of the numbers from it. Yes?
What do these complexity classes mean in terms of Sudoku? Like, what's like the varying size for Sudoku?
Sudoku, that would be, I suppose, the size of the Sudoku.
It's always a 9 by 9.
You can increase the number, like to the max number. Instead of it being 9, you make it some square number.
I see. So in that case, we're not doing like that 3-grid rule. That would get confusing.
Yeah. To be honest, I know this result without knowing how they formulated it. So they may formulate it differently than I just said, but I know the result. Okay, who thinks it is exponential time? Who thinks it is NP? It's pretty easy to check a Sudoku. Who thinks it's in P? And who thinks it's in linear time? It is, in fact, proven to be in P. Yeah, very interesting one. It was for a long time considered one of these problems that was in NP that isn't in P, but it is not. It is not one of those. We'll talk about later on why that doesn't mean that P equals NP, but it doesn't. It's in both. Yeah. Okay. Next up, halt. So given a program with n bits, determine if it will ever finish running. Who thinks this is exponential time? Who thinks it is NP? P. Linear. No one. It is, in fact, none of them. So this is the halting problem, which hopefully you've heard at least that name before. It is famously undecidable, meaning that on a classic Turing machine, or in fact a non-deterministic Turing machine, it is impossible to decide whether or not a program will finish in general. There is no relationship to the size of the problem either. Yes?
Wait, what does the question ask for?
What?
Say if there's like a program.
So if I give you a program, you just have to determine if the program will ever finish executing. Like, is there an infinite loop in it, basically? And famously, this problem is undecidable, which means that a Turing machine cannot compute it in general. So that is our classic computers cannot decide whether or not it halts. Yeah, an interesting problem, and it shows that computers are not all powerful. Next up, last one on the front side, factorize. So given some integer n, find all of its factors. Okay? Who thinks this is exponential time? NP. Polynomial. And see exactly who doesn't think P equals NP, which is fun. And then linear. Okay. It is, in fact, exponential, NP, unknown if it's in P. It's unknown if it's in P. So we have, in fact, we have sub-exponential algorithms to find, you can go ahead and look it up yourself if you'd like to. We have sub-exponential algorithms to find this, and it's pretty clear that it's in NP if you think about it for a little bit. Given this list, multiply them together. If you get your number, then you've verified it. But in fact, we do not have a polynomial time algorithm to factorize. Yeah?
Does that mean
I don't think it means that. You can look up the problem on your own. I just know it's just considered non-polynomial.
It's defined in terms of like the length of the number,
Yeah.
not
Yeah.
like the value of the number.
okay?
Yeah. Okay. There. Yes.
What about the halt one? Like,
Yeah.
how are they even like?
How could we show that
Are
like?
they like? Are they looking for errors? Like
So we can't do it. That is sort of the result of the halting problem, is that there is no algorithm to check that. There's no algorithm that will ever tell me guaranteed that it will finish, which is an interesting result. It's an interesting problem. Yeah. Mm-hmm. So Thomas was saying that this is defined in terms of the length of the integer instead of the actual absolute value of the integer. I actually am not super. I just was looking up problems that I was familiar with and saying, oh, what's the runtime of each of these to make up this. I made this in about 15 minutes, by the way. So sorry if I didn't do thorough research on it. Look it up yourself online. You'll see how it's defined. It's a good catch. I think there were a bunch of people who were upset by that answer. So it very well could be the case that that is correct. So it's perfectly fine. Yeah.
How do you like to
So we do know it. We have an algorithm. We have a runtime for an algorithm. We don't know if it's the lowest it can go. Yeah. So if it could be that we could come up with a faster algorithm that does run in polynomial time, but we don't know if we can. The algorithm that we have so far is not polynomial time. Yeah. There's going to be a lot of things like that, by the way. A lot of problems that we're going to talk about in NP, we don't know if it's possible to solve in polynomial time. We already ran into one here. Okay, now, I know that, who attempted the bonus? Okay, not many people. I'm going to ask, yeah?
It's sort of like, so you can't even store a pointer, right? Because like,
You can store a pointer.
so that would take logarithmic space, right? Because like you want to like store the value of like the index.
I mean, you don't need a pointer. Okay, so I am going to ask that everyone also attempt the problem on the back. I'm not going to give you the full answer in terms of the algorithm you have to write, but I want everyone to make a guess as to the complexity class that this is in. Yes. Is what sort? Yes. Yes. N log n is polynomial. Yeah. Okay. Everyone, attempt the question on the back now. You can talk to people if you'd like to.
Let's say you have like a thousand to store the size, to store any like index in that array, you need 4 digits, which is log base 10. That's not even constant.
I think because of the store.
Well, if this space depends on like the numbers, then you can store it constant.
Oh, I get it. I see what you're saying. You're just storing an integer.
Yeah, but storing an integer that's like within the size of the array would take like n log n. I'm not, and what am I saying n log n times? Sorry, I don't know why it's those words. I see log space.
Technically, yeah, that is true.
Because like if you have like if your array is like 1,000 long, right? How many digits do you need to store any individual?
I see.
3, right? Or like 3 or 4, depending on if you're including that one. And then that's log 10 of 1,000.
Technically, yeah, that is true.
Maybe you should have said log 10, but like I don't know.
Well, is that something that's considered though in you look at algorithms, like, not consider it constant time? Constant, sorry.
The whole algorithm is
The whole algorithm cannot use 1 My first input as
That might be how you do it.
yeah.
I'm assuming you like video bubble sort and constant space.
Well, no, iterating or expanding is not at the same. What? I think it's not all your mind. It also you can
Okay, I'm going to cut you off there. Same game as the previous one. I'm going to have you raise your hand if you think it's in a class and put it down when you think it's not. Exponential time. As most people. NP. Polynomial. Linear. Okay. So, as some people have pointed out, it is possible for you to do in-place operations, just as something you point out. If I wanted to swap elements of it, I can do that. You have to be somewhat careful with storage. When we're doing constant storage, it can be tricky, but we can do stuff like that. And it is, in fact, doable in linear time. So, I'll leave you with that. If you'd like to attempt the rest of the problem, you now have a bit of a hint, I suppose. And you've thought about it a little bit. I'd recommend doing some of these bonuses. They expand your brain. Okay, now, Any questions before we start? We're gonna tease the next topic, but I'll answer questions now. Yeah. No. Okay. It would be very easy then. Yeah. You can iterate. Yeah. That takes O of n time. Yeah. You can just iterate. That's fine. That's fine. You're just going to be adding to the thing. Yeah. So for space complexity, it's okay. It's okay. Yes.
Did you say if there's like n elements? Like n linear?
Non-deterministic linear exists, but is not relevant to this class. And you can look it up if you'd like. You can look up all these complexity classes if you'd like. I think I'll throw the diagram up at the end again, just so you can look at it and contemplate. Any other questions? Yes.
What is like the big
I mean, that is definitely one thing. I think the existence of this complexity classes, the thing that I can say a certain problem is in a certain complexity class, what those complexity classes mean, especially this bottom one. This bottom one is the thing that is not intuitive to anyone. And then also knowing the hierarchy of them is also helpful. Knowing this hierarchy of runtimes is a definitely takeaway. Yeah. Okay. Any other questions? Okay. So I have been making things easier. You've seen the diagram. You know that I've been simplifying things a little bit. There's a particular way that I've been simplifying things, though, that I want to make clear because it will be really important for next lecture. So when we're talking about these problems, the way that these classes are defined is in terms of decision problems. So what we have here are not decision problems, for the record. Decision problems are problems that only have an answer yes or no, true or false. So it's for example, it would be, is there a maximum, is there a longest simple path with length blank? That could be my question. And the answer to that question is either yes or no. And it turns out, yeah?
You said that these are the halting problem be a decision problem?
Yes, it is. Yeah, it is. Yeah, but it's an undecidable problem, which sort of takes precedence when it comes to that one. But yes, it would be a decision problem because you're saying either yes or no. So yeah, we're going to, from this point on in class, basically, we're only going to be talking about decision problems, but fundamentally they are the same still problems. Yeah.
The Sudoku problem is a decision, but yeah, most of them
Yeah,
are not.
most of them are not. I'm saying they are not properly formatted for talking about complexity. From now on, we will be doing that. I just wanted to keep it somewhat familiar for you guys to start. And now, from now on, we're going to be talking about decision problems. So only problems that say yes or no. That is, given this array, is this a sorted array? For example, would be a decision problem, although a dumb one. And it turns out that there is actually a difference between the difficulty of returning yes correctly and returning no correctly. So, in fact, this here, NP, the class, is actually the class of problems which I can return in non-deterministic polynomial time a correct yes answer. So that is, if it is solvable, if the answer is yes, and I can return that yes with full correctness in polynomial time, non-deterministic polynomial time, then I say that it is an NP. But that does not mean that if the answer is no, that it will ever return an answer even. You understand that? So there are problems that so these decision problems, yeah?
I think it's simpler.
I mean, sure. We'll talk about that more next class. But I'm gonna teach it this way. So if I have a problem, if I am able to verify correctly that the answer is correct, which is getting a little bit at what you're saying, certificates. If I'm able to say, given this hint, that it is in fact true, then I would say that it's an NP. If I can get some verification, I can say it is incorrect, and that the problem, that is not the answer to the problem, then I'd say that I can answer no in non-deterministic polynomial time, and I call that class co-NP. So co-NP is the non-deterministic polynomial class where I can return no correctly in non-deterministic polynomial time. Okay? So we'll have examples of this next class, and we'll talk about some other features of these next class. But for now, I want you to just realize that, in fact, our picture is slightly more complicated. So, in fact, there is now two little bubbles here. So instead of it being just, we'll now have NP is one bubble right here. So NP is the class of problems. It still totally contains P. In P, we can say yes or no in polynomial time. Obviously, we can check in polynomial time then. And can anyone tell me where co-NP would go on this? Yes.
The opposite of
Exactly. So co-NP will be possibly disjoint. Sorry, I had to draw it weird to make it disjoint. Give me a second. Say that this is NP, and we can say that this then is co-NP is something like this, right? So co-NP, not outside of exponential, sorry. Co-NP is going to be a separate group of problems than those in NP. It still could be the case that NP is equal to P, and if that is the case, in fact, co-NP is also equal to P. Okay? That make sense? Yes.
I think it's also possible for NP to equal co-NP, but there's like a bunch of possibilities.
Yeah. There is possibilities. So it could be the fact that we could have that there is a set of problems that are both decidable yes and no in non-deterministic polynomial time, and that they are not decidable in polynomial time. Is what
It
Tomas
could
was
also
saying.
be that the intersection is P, or the intersection like has something that does not include P.
Yeah, that's where the diagram gets complicated. Yes.
I've heard the term NP before.
Yes. So NP hard is everything that is harder, that is takes more time than NP. Than every problem in NP. We'll properly define this on Friday. For today, I'm going to leave that vague. I think that's fine. But it basically means that it is harder than NP. Harder than or equal to NP. And we'll see exactly what that means. Any other questions? Yeah. Sure. There is also still. I'll throw up the diagram because I said I would. We can see exactly what it looks like on the complicated diagram. There are simpler versions of this, by the way. All right, but I'll pull this up just so you can look at it again and now appreciate it with some more information, some more context. Okay, give it 1 sec. Sorry. Yeah, well, we'll talk about it a lot more next class, though. We'll have diagrams. We'll have a lot more clarity on this stuff. Don't know why it's taking so long to log in. Yeah, any other questions? Yeah.
Does linear time and linear
I believe they're equal, if I'm not mistaken, but they might not be. I don't know why it's not loading. Give me a second. You can also find online, if you'd like to, you can look up, this is descriptive complexity. You'll find that diagram in all these. Hang on 1 sec. Okay. Sorry, that was weird. Should come up in a second. Yeah, you can see we can zoom in on the on the actual area that we care about. So this right here, you can see is P. Then we have this is the intersection of NP and co-NP. They might intersect. We don't know if they do. Then we have and yeah.
They definitely intersect. It just
The intersection might just be P. Yeah, exactly. It could be that there exist some problems that exist here that are not in P, but we don't know if they do. We also have, so co-NP and NP are sort of separate from each other. If you want what this diagram looks like if I take out some of the noise, it's basically that we have, here, I'll give you a simplified version. Here, with P, we have, this is NP, this is co-NP, and then there's some intersection hypothetically. We don't know if there is one or not. And then there are some problems here which we will talk about quite a lot. Those problems are NP complete and co-NP complete, which we'll talk about in in some time. And then above all of this, in all this, there's some region here which we're not going to talk about, and then there is, on top of all this, exponential time. The exponential time is strictly larger. You can imagine these as our circles too. You can say that this is the smallest circle, and then they sort of go outward, but this ends up being a little bit complicated because then we have, if that's P, then we have two circles that may have an intersection, might not. P, co-NP, and then we have exponential is everything. So that's another diagram of what we have here. And there is, in fact, more that we're going to care about, but not much more. Okay? And then you can sort of take a look back. You can see where halting problem is up here, in case you're curious. And you can see some other problems that you might recognize, like too colorable down here. Look at that. Okay, cool. What? Okay. All right. So the next thing that we're going to do in class on Friday, we're going to start talking about how we can show that we're going to do a couple examples of showing things are an NP, and we're also going to be talking about this class. Basically, the entire next lecture and maybe the one after that is going to be talking about not co-NP complete, but NP complete and some co-NP complete problems also, and how we can show what those are. To give you a little bit of a primer, those are problems that are in NP, so they are non-deterministically polynomially solvable, or co-NP solvable, but are the most difficult problems in that class. So to have completeness is to be the most difficult problem in a class and to be in that class. Okay? To give you a little bit of a primer, it's an interesting thing that we know that any of those exist, and what we can do with them is also very interesting. So we'll talk about that on Friday, and then possibly again next Monday. Any questions before we call it a day? Yeah. Very cleverly. We'll show what we can do. We get to build off the shoulders of giants is the short answer. But proving that a problem is the hardest problem is very difficult. Proving that other problems are the same difficulty is much easier. Yeah.
I was just going to say, are they all
So it's a class, not a single problem, and that in fact is because there are multiple that are equally difficult. And we'll show what that means. All right. Any other questions? All right. Enjoy the day. Goodbye. The next homework. So I haven't 100% decided. Seam carving was the idea, though. Yeah, it's a discussion. Yeah. But we're going to do it on images, large scale, automatically. Yeah. Yeah. Cool. Run.